Okay, so this is a review for the first part of Unit 3. Some of this should be a review from Algebra 1, but not all of it, so heads up. So first off, it asks, is this relation a function? So relation is just any set of ordered pairs. Is this relation a function? What we should be looking for is if all of the x's are unique, and I see here and here that 5 repeats, and it is not paired with the same member of the range. And each member of the domain must have only one member of the range paired with it, and so since 5 has 2 pairs, this is not a function. The inverse of the function means the opposite, right? So this is all of the x's become y's, all of the y's become x's, so it is just a big old switcheroo. So the inverse of this function, I'm just switching each ordered pairs, the x and the y are going to switch like that. Simple enough, right? And then now it asks, the next thing it asks is it a one-to-one function? So to be one-to-one, reminder, this is a review. This should not be the first time you've heard this. But if it is one-to-one, the relation itself must be a function, and the inverse must be a function. So in this case, the inverse actually is a function. However, that does not matter because the original function. So no, it is not, because the original function is not, because the original relation, I should say, because the original relation is not a function. So if it is not a function to begin with, it absolutely cannot be a one-to-one function because it's not a function at all. Right? So one-to-one is a special kind of function. If you're not a function already, you can't be a one-to-one function. All right, next up, another one about functions. Let's get rid of that, show us a little more space here. So on number 2, again, we're asking, is this relation a function? And as I look through the x's, they are all different. So in this case, yes, it is a function. The inverse, so now I'm going to switch my x's and y's. So the original is a function. Is my inverse a function? Yes. You don't need that for part B, but you need it to answer C. And then is the original relation a one-to-one function? And we would say yes, it is, because, or you could say yes, it is a function, because both the original and the inverse are functions. So 2 yeses mean yes, it is a one-to-one function. All right, so there is your first couple questions. Hopefully you feel like easy peasy, lemon squeezy. And number 3, we have 2 graphs, and we are asked if the graph represents a one-to-one function, and if it does or does not, you are supposed to also tell how do you know. So just a yes or no does not earn full credit on these questions. So for the first one, to know if it represents a one-to-one function, remember that if it passes the vertical line test this way, vertical lines, if a vertical line that moves across only touches one place at a time, which it does, it passes the vertical line test. And then what you would want to do next is keep in mind if the x's and y's were switched, it turns it kind of on its side, so to speak. And so now we would want it to also pass the horizontal line test. So now we go across this way, and again, nothing should be the same. It should only be touching one place at a time. In this case, it passes both, so yes, it is a one-to-one function. So yes, it is a one-to-one function. And we could use because, or we could simply say it passes both the horizontal and vertical line tests. You could give those two things in whichever order you want, but it's passing two tests, not just one. And then the second one, same idea. So if I come across with vertical lines, pretend this is one vertical line moving across, each of those vertical lines only touches in one place. So it's passing the vertical line test, but when we start doing horizontal lines, whole bunch of nope, right? So it does not pass the horizontal line test. So here I would say, no, it is not a one-to-one function. And then if it's a no, I just need to tell what it fails. So I'm going to say it fails the horizontal line test. That's the one that goes side to side, like the horizon in the sky. If you also want to tell me that it passes the vertical line test, okay, but since you're saying no, we need to tell why it's a no. It fails the horizontal line test. All right, page 1 is done. All right, next up we're talking about the inverse of functions. So our steps when we're doing inverse, remember inverse, we are switching x and y. And so first I need to recognize that f of x, this function notation, means the same thing as y. I haven't switched anything yet. I'm just using a different notation. That's the same function as originally. Now I'm going to actually do the inverse and switch x and y. So now x is here and y is up there in the fraction. And then at this point, remember, you want to do everything that has to be done to get y by itself. So this is probably feels a lot like if you were doing slope-intercept form or solving literal equations. So to undo the divide by 9, which is what has to happen first, I'm going to multiply by 9. So now I have 9x is equal to y minus 1. And if I want that y by itself, you got it. I got to get rid of the -1, so I'm going to add 1. Or you might just think that you're moving it to the other side, and when it crosses the line, it changes its sign. So at this point, the y is by itself, but we're going to give this answer in function notation. And inverse, we use the same letter. So if it's the f function, we're going to use the f, but we use this -1 to show inverse, and still so it's raised up kind of like an exponent. So here, I'm just going to go ahead and write that first. Inverse of f of x is equal to 9x plus 1. And this, my friends, would be our final answer. So that last part is just a little notation part, but to get full points, you would be expected to do that. All right, we have another one here. This time we have a cube. So again, we're going to put the y here. And now we're going to switch x and y. So then this will become x equal y cubed minus 4. So remember, you're working opposite operations in the opposite direction of order of operations. So order of operations, adding and subtracting, are last unless they're part of a fraction like what we had before. And so here, that's going to be the first thing. We're going to get rid of the 4 first. So we're going to add 4 to both sides, getting rid of that -4. So x plus 4 is equal to y cubed. And now, to get rid of cube, we use the root. Roots and powers are opposite or inverse operations. So it's a third power, so we use third root. And whatever I do to one side, you know it, I got to do it to the other side. And everything that's on that other side gets the root. We don't do the root until the variable with the exponent is alone. And so that cube root and cubed just get rid of each other. So really this looks very much the same. And then we're just going to change out our notation. It's not a problem if you leave that on the right, but typically you would see it on the left. And then it should be obvious that the 4 is under the radical, because it can be on the outside. So it needs to be clear that that radical is extending above the 4. And there is our second inverse problem. Next up, you have a couple of factoring problems. These are very specific types of factoring that involve the pattern for difference of cubes or sum of cubes. So you might remember that we used difference of squares previously. And so this first one actually falls under a difference of squares, the bottom two difference of cubes. So for the first one, we should always do GCF first if we can. And so here I'm going to do GCF. And then after I do GCF, I'm going to think about difference of squares and how that factors to be the sum and the difference of those two terms. So 32 and 162, well, they're both even, so let's go with 2. Also, I might be thinking, maybe they're supposed to be perfect squares. So I'm going to divide both by 2, leaving us with 16c to the 4th. Notice I don't divide the exponent by 2 there. This is just a common factor. And this looks good because 16 and 81 are perfect squares. But we have a 4th power instead of a 2nd power. So when we're working with exponents, any even exponent is a perfect square because you can split it into 2 that are the same. So this 2 on the outside stays part of our answer, and then we're going to follow our difference of squares pattern So for this first part, I'm doing this. So the square root of 16 is 4. They both get a 4. And c to the 4th is going to make this c squared in both cases. Then I move on over to my 81. Square root of 81, well, it's negative. We know the pattern also tells us 1 plus 1 minus, and the square root of 81 is 9. Now at this point, you should look at it once again to see if perhaps you still have a difference of squares, because if you do, you need to factor some more. Remember that when we're talking about squares, the sum of squares does not factor. So now the 2 for the GCF and the sum of the two squares, 4c squared plus 9, just drops down. But then this fella, he can now go again. So 4c squared is still a perfect square. So 2c and 2c. We know there's going to be 1 plus and 1 minus. And then 9 square root of 9, 3, and 3. These things could be in different order, but you should have a GCF and then 3 sets of parentheses for this factoring problem. Okay, awesome. All right, number 7. Number 7 and number 8, now we're to our difference or sum of cubes. So with cubes, we can do it whether it's plus or minus. With squares, only works for minus because there's only a difference of squares pattern. And you'll have this, so you are not required to memorize it, but this is our pattern for the sum of cubes, that when we factor it, we have the square root of both of them, and that sign will match our original sign. And then we have a trinomial, and that trinomial, we square the first, we square the last, and then in the middle, we have a combination term with a negative sign. Oh, and this is a plus at the end, my bad. So that middle sign will always be the opposite sign. And if you're not sure, just like any other factoring, you could multiply it out to see what you get. But what you'll see and why that's different in the middle is so that things cancel out and we are only left with a cubed and b cubed and no a's and b's together. And very similar, if it is the difference, that means there's a subtraction in the middle at first. So the little one, the sign matches. And the big one, still a squared and a squared. And then the combination term that's in the middle is the opposite. So if you notice, those two patterns are not very different from each other. The only difference is this sign and this sign. The little one matches, the middle of the big one is the opposite. Again, you do not have to memorize those, but you want to think about those patterns as you answer these questions. So first thing we want to think, are they perfect cubes? So we're looking for exponents that are things like 3 or 6 or 9, some multiple of 3 now. And then third power, perfect cube. So we will have talked about, our perfect cubes. So in this case, x cubed, well, then that means that a is just x. And 125 is 5 cubed. So x plus 5. Once you have that x plus 5, you can think of the x and the 5 being the a and the b. So the first part is supposed to be a squared, so it's x squared. Change the sign in the middle. Now multiply them times each other. 5 times x, 5x. Now square the b. That's it. Easy peasy. Okay, number 8 is a little more challenging because the first variable also has a coefficient. And so we would need to use our calculator or make a list of perfect cubes so that we could find it, or maybe you just recognize it. But 64 is 4 cubed. So this is like saying 4a cubed. 343 is 7 cubed. 7 times 7, 49 times 7, 343. Yeah, it gets big quick when it's exponents. So it's like that, basically. You don't have to write that anywhere, but it may help to think about that. So then my little one is kind of just what I wrote up here without the cubes. It's the 4a, and the sign matches, and the 7. Now thinking of this as being a and this as being b, 4a squared means 4a times 4a, so 16a to the second, not just 4a to the second. In the middle, the sign will be opposite, and then we need to multiply a and b together. So 7 times negative 4, or 7 times 4a, 28a, because we already said it's going to be the opposite sign. And then we square the 7. So 7 squared plus 49. And once again, if you are not confident in your factoring, you all are great at distributing and multiplying. You could distribute things out to check to make sure it works. We will have done a couple of those in class, and you should see that some things cancel out so that all you're left with is 64a cubed minus 343b cubed. Oh, except that you would not have that because I left off my b's. It's a good thing I was talking about that, or I would have left that way. So here, where this is 7, it's not just 7, it's 7b. And this isn't just 28a, it's 28a. B, and this isn't just 49, it's 49b squared. And I'm like over 20 minutes into this video, so I am not backing up and starting over. Forgive my error, and I'm glad I caught it before I was finished. As I started thinking about, as I multiply this would happen. Without those b's, it wouldn't have happened. So there you go. Everybody makes mistakes, but try not to let the mistake happen to you on your actual quiz. All right, coming into the home stretch here. Now we're going to talk about functions and different operations with functions. So you have 3 functions at the top of the fit page. We're going to call those the F, G, and H functions. And then we are to answer the following, which means we may have to add, subtract, multiply, divide, or compose. And then we are also to identify if there are any restrictions. Restrictions meaning numbers that x is not allowed to be equal to. So here we go. So the first one just says f plus g. So it's just addition. So we are just going to be combining like terms. Personally, I probably would write x squared plus 4x minus 12. And then I'm going to add g to that. So I'm going to put 5x squared and minus 2. And then put them in some columns. They don't have to be in columns. You could just look up top and combine your like terms. But it is very much just a combining like terms. All right, so that is what f plus g of x is equal to. The only time we're going to need to worry about restrictions is when we have division, and remember that the denominator cannot equal 0. So that's going to give us our restrictions on the domain. So number 10, f over h. So f is going to go on top. H is going to go on the bottom. Now, technically, I should factor the numerator, because if I could cancel something out, I would. But in this case, this would factor to be a plus 6 and a minus 2, and neither of those would cancel with the x plus 7. So it's not really an issue, but I do want to acknowledge that sometimes that could be different. Not going to be on this quiz, but just looking ahead to the next unit. So this is my f of h, f over h of x, and my restriction x cannot equal negative 7. So to get the restriction, take the denominator only, equal to 0. So that means negative 7 makes the denominator 0. We can't divide things by 0. So that is why it is a restriction on the domain that it is not allowed to equal that number. All right. So next up, in number 11 and 12, hopefully you notice the difference between those two. They are not the same symbol. The first one, when the dot is filled in, that is our typical multiplication dot. And I need to get back up here to get the functions. So we've got x plus 7 and 5x squared minus 2. All right. And this one is G, and this one is H. Okay. I don't want it to be so small, so just have to jot that down. All right, so H times G, you would put them both inside parentheses. The parentheses are touching. We are multiplying, and so we would do all of the distributing steps. So I'm going to go x times 5x, 5x cubed, x times negative 2, negative 2x. X is done multiplying. Now it's 7's turn. 7 times 5x squared, 35x squared. And 7 times negative 2 is negative 14. Then I would just tidy this up a bit to include my label at the front. If you forget the label at the front, which I think I may not have written number 9, but this is just my label. And then I would put this in standard form, not quite like standard form of a quadratic because it's a cubic, but highest exponent down to lowest exponent. So 35x squared and negative 2x are going to trade places so that it's in descending order from the highest power to the lowest. All right, fantastic. On the next one, now we are doing composition. So this is where one function, the second function, goes into the first function. So in this case, the h function is x plus 7. That is our h function. So my g function, which is 5x squared minus 2, this entire g function is going to substitute in for that x. Just like any kind of substitution, once we put it in, the regular x is no longer there. So now what we have for h dot g of x is 5x squared minus 2 plus 7. And then we go ahead and simplify what we can, which in this case makes that 5x squared plus 5. And then the last two questions, we have a number, and you could perform the operation on the functions first and then plug in the number, or you could plug the number into both functions and then perform the subtraction. I feel like especially for a composite, for number 14, it's definitely easier to plug it in and then plug the number in, but you should get the same answer either way. So for 13, we have a subtraction. If I plug 4 into both of them, so if I plug 4 into 5x squared minus 2, if I plug 4 into 5x squared minus 2, because that's my g function, then this is 5 times 4 squared minus 2. So that's 5 times 16. That's 80 minus 2, 78, right? You could just type that in your calculator. Notice the squaring happens before you multiply by 5. And then if I do h of 4, h is just x plus 7. So x plus 7 becomes 4 plus 7. This is 11. Subtraction in the middle. So now I'm going to subtract those. 78 minus 11 is 67. Number 14 is our composition one. So think about, this is, although also do not try to use what you did in number 12, because it is different if the order is different. Compositions are not commutative. The order matters. And so here we're going to take -5 into the h function. So the h function is x plus 7. So we're doing -5 plus 7, which is 2. That number now, this answer is now going to go into the g function. And the g function says 5 times 2 squared minus 2. So that's 5 times 4, 20 minus 2 is 18. And notice for these, we get final answers that are numbers. So if we are evaluating the function at this number, then our answer is a number. It no longer has x's in the answer. All right, that's a little longer than some of our other reviews. I hope that was helpful. I'll be seeing you in class. Thanks.